Welcome to Mrs. Z's Chemistry. In this video, we will learn about hydrogen bonding. So far, we've learned about two of the three intermolecular forces. All molecules experience London dispersion forces, abbreviated LDF. Both nonpolar and polar molecules experience this type of intermolecular force, or IMF. However, nonpolar molecules only experience this type, this London dispersion force. Dipole-dipole interactions or attractions are experienced by polar molecules. Hydrogen bonding is a special type of dipole-dipole interactions, and this is when hydrogen is directly bonded to nitrogen, oxygen, or fluorine. This is because the bonds between hydrogen with any of the nitrogen, oxygen, or fluorine is very polar. Even though we call this hydrogen bonding, the word bonding is a little misleading as it is not a bond like a covalent bond. Covalent bonds are still about 10 times stronger than the IMFs of hydrogen bonding. Let's look at this picture a little closer here. This red hydrogen right here is covalently bonded with the solid black line to oxygen in its own molecule, but it's also attracted to the oxygen of the neighboring molecule that is also directly covalently bonded to another hydrogen. So these red dots here indicate the hydrogen bond that's happening between this. So where you're looking for a hydrogen sandwich, you have a hydrogen in the middle, you have a covalently bonded oxygen and a hydrogen bonded other oxygen from another element or from another molecule. This can happen with any element of nitrogen, oxygen, or fluorine that's directly bonded to hydrogen. So here's the red hydrogen here that is directly or covalently bonded to nitrogen in its own molecule, but then it's going to be attracted through hydrogen bonds to the nitrogen of the neighboring molecule that is also directly bonded to at least one other hydrogen. It doesn't have to be two of the same molecule. It could be two different molecules as long as each molecule has hydrogen directly bonded to either nitrogen, oxygen, or fluorine. So here's another picture of how hydrogen bonding works in water. You have hydrogen directly bonded to the oxygen in its own molecule, but then the hydrogen bonds are the attraction between that hydrogen and a neighboring oxygen from a neighboring molecule. Let's look at some data that shows that hydrogen bonding exists and that it is in fact much stronger than dipole-dipole or London dispersion forces. So along the y-axis on this graph here, we have the boiling point temperatures in Celsius from negative 150 to positive 150. Along the x-axis, we have the periods or the rows, the horizontal rows on the periodic table. Second row, third row, fourth row, fifth row. So starting at the fifth row or period on the periodic table, we're going to look at these molecules that are, or the elements that are bonded to hydrogen. So if you pull out a periodic table, you can see that tellurium would prefer to make two bonds, so it makes a bond or a molecule with two hydrogens. Sb, or antimony, makes a molecule with three hydrogens, and iodine makes a molecule with only one hydrogen. So all three of these on this graph have the highest boiling point, and that's because they have the highest amount of electrons. When molecules have more electrons, then they are more polarizable and have stronger intermolecular forces, requiring a higher boiling point or more energy in order to break the molecules from the liquid state and turn them into a gas. So if we move up on the periodic table to period 4, then we can see that the molecules are going to be a little bit smaller because we have less electrons and their boiling points are going to be a little bit lower. Because again, there are less electrons, so the intermolecular forces are weaker. We see the same trend happening when we move up on the periodic table one more time to the third row on the periodic table. These molecules have even lower boiling point. Following this trend, we would expect the molecules from row 2 or period 2 on the periodic table to have the lowest boiling points as they have the lowest number of electrons out of all of these molecules. However, experimental evidence actually shows us that the boiling points of water, H2O, HF, and NH3 are much higher. So this shows that the intermolecular force of hydrogen bonding is much stronger than dipole-dipole. which means molecules that experience hydrogen bonding require more energy to break apart to turn into a gas, which means they have the higher boiling point. Hydrogen bonding holds DNA together. When DNA splits apart to replicate, it's the hydrogen bonds that break apart. So let's look at this a little closer. If you remember from a biology class, there are 4 bases or nitrogenous bases that DNA is made up of. We have guanine, cytosine, adenine, and thymine. And between these pairs are what's holding them together, hydrogen bonds. You can see that guanine and cytosine each have 3 places for hydrogen bonding. Thymine and adenine each have 2 places for hydrogen bonding. And that's why these specific bases, the A and the T and the G and the C, are paired together because of the amount of hydrogen bonding places that they can each make. When DNA splits apart in order to replicate, it splits apart across the DNA or the hydrogen bonding middle. And that's because hydrogen bonding, while yes, it's the strongest intermolecular force, it's still way weaker than the covalent bonds. The covalent bonds are the solid lines here that these are not going to break because they're so much stronger. So the actual molecules aren't breaking apart, just the hydrogen bonding that's keeping the molecules together. Pause to see if you can complete these problems. Here are the answers. You can pause and read through these and see if these make sense. Here are some definitions of phase changes between gas to a liquid, liquid to a gas, and so forth. Here's a picture representing the relative amounts of energy from each phase change. This word enthalpy can mean energy in this context. Energy of the system increases as it moves from a solid to a liquid to a gas. Here's some characteristics of the different phases, gases, liquids, and solids. The most important thing from this slide is to see that gases are compressible. You can compress a gas into a smaller sized volume or a smaller container without the gas turning into a liquid because the molecules are so far apart from each other that even when they're compressed, they're still far enough away from each other that they do not feel any attractive or repulsive forces or intermolecular forces between them. A liquid and a solid, however, are both basically incompressible. The liquid particles and the solid particles are so close together that you can't really compress it anymore without breaking the liquid. In other words, turning the liquid into a solid, or breaking the solid and actually shattering the solid object that you're holding. This is a great slide to look at to remember all of the intermolecular forces. Boiling point, or the temperature at which a substance boils, increases with increased polarizability, which comes from increased number of electrons. Boiling point increases as the intermolecular forces increases in strength. So if you are comparing molecules with similar number of electrons, a molecule that experiences hydrogen bonding is the strongest, and only London dispersion forces, or LDF, is the weakest. So let's go ahead and put the following substances in order of decreasing boiling point. Decreasing boiling point means you start with the molecule that is the highest boiling point and work your way down from there. First, we need to determine which intermolecular forces each one experiences. Water experiences hydrogen bonding because it has hydrogen directly bonded to oxygen, nitrogen, or fluorine. So hydrogen, or water, is has the highest boiling point because it experiences the strongest intermolecular force. NO is a polar molecule, therefore it experiences dipole-dipole interactions as well as London dispersion forces. N2 is a nonpolar molecule and only experiences London dispersion forces, which is the weakest force. Therefore, it doesn't require nearly as much energy or as high of a boiling point to turn the liquid into a gas. Put the following substances in order of decreasing boiling point. So here's a hint. If all the compounds experience the same intermolecular force as they do here, all 3 of these molecules only experience dipole-dipole interactions as well as London dispersion forces. But they all experience the same level of strength of intermolecular force. So then we need to find the molecular weight or mass of the molecule. And this is because the heavier the molecule, the more electrons it has. Therefore, the more electrons has the stronger intermolecular forces, which leads to the higher boiling point. If you were to add up the molar masses, we can see that NF3 has roughly a 7 grams or 71 grams per mole. SiS is around 60 or 61, I believe, and carbon monoxide is, carbon is 12, oxygen is 16, so that's around 28 grams per mole. So that means NF3, because it has more electrons coming from the fact that it has a greater molar mass, has the strongest intermolecular force, or the strongest dipole-dipole interactions. SiS has the next strongest, and then CO is the weakest, because it has the fewest electrons. Which one has the highest boiling point? Pause to see if you could work this out. So the first thing you'd want to do is figure out which intermolecular forces each of these molecules experience. We're just going to list out the strongest intermolecular force that each molecule experiences. CH4 is nonpolar. pH3 is polar, so it experiences dipole-dipole. NH3 has hydrogen directly bonded to nitrogen, therefore it experiences hydrogen bonding. H2S is polar, therefore experiences dipole-dipole. And H2O has hydrogen bonding. So you can see we can easily cross off these three, and we're left with either NH3 or H2O. The answer here is H2O. If you add up the molar masses, NH3 has a molar mass of 17 grams per mole, and water has a molar mass of 18 grams per mole. Now that molar mass difference alone is not enough to explain how much larger water's boiling point is than NH3. There's a lot more complicated chemistry going on, but for right now, just adding up the molar masses is enough to tell you that water does have the higher boiling point. Viscosity is the resistance of a liquid to flow. So in other words, maple syrup or oil have a higher viscosity than water. And honey is even more viscous than maple syrup. Viscosity is related to the ease with which the molecules of the liquid move around each other. It depends on the attractive forces between these molecules, which are the intermolecular forces. So the stronger the intermolecular forces, the more viscous the liquid. Liquids that mix in all proportions, such as acetone and water, are miscible, and then liquids that don't dissolve in one another are called immiscible. Gasoline, which is a mixture of hydrocarbons, which means molecules that have just hydrogen and carbon, is immiscible in water, and that's because hydrocarbons are nonpolar and water's polar. Nonpolar liquids tend to be immiscible in polar liquids. So looking at this picture, you can see the water is floating on top of the water. The oil is floating on top of the water. That's because oil is a mixture of hydrocarbons, and so it's not going to mix or be miscible with water. So you can think of it this way. Like dissolves like, and that means polar liquids dissolve other polar liquids, and nonpolar liquids dissolve other nonpolar liquids. So here's a good summary of all of the intermolecular forces that we've learned. Nonpolar molecules experience London dispersion forces, which can be abbreviated as dispersion forces or LDF. Polar molecules experience dispersion forces and dipole-dipole interactions. And molecules that have a hydrogen directly bonded to either N, O, or F, spelled backwards, you can think of this as the fun elements. They experience dispersion forces and dipole-dipole, of course, and also hydrogen bonding. So they experience all three intermolecular forces. Another good way to put this is saying nonpolar molecules equals dispersion forces, polar molecules equals dipole-dipole and dispersion, and then the polar molecules with hydrogen directly bonded to one of the fun elements is all three intermolecular forces.